Hello, am I audible? Alright, so I'll start now. So, first I'll begin with the basics of the segment tree. For those who do not know much about the segment trees, so segment tree is basically a data structure to do range some queries and range update will be done later. First we will do point update and range get queries. Like if we have an array, here we have an array. If we want to like update a specific index on it, then we can update that using the segment tree. And if we have a query like input of 1 comma 5 and we need to get some property in this range, like if we need the sum of elements in this range, then we can get the sum of elements of the range using the segment tree. So how do we do this? um, like 1 second. So basically, we store an array and we make a binary tree on it, complete binary tree. Without loss of generality, assume that the array size is a power of 2. So what we do is um, we combine the nodes in pairs of 2, like both bottommost, these two pairs are combined into a single node, these two pairs are combined into another node, and so on. So basically, like this node This node here represents the sum of elements of these two nodes. First we are considering range sum queries. So like this is 5 and this is 8. This is our original array. If we consider the node represented by first two indices of the array, we get this node. The third and fourth indices correspond to this node. 6 plus 3 equal to 9. 2 plus 7 equal to 9. 2 plus 6 equal to 8. So then these two nodes then this node corresponds to this entire range, all the indices stored in its subtree. So the sum of this range is 5 plus 8 plus 6 plus 3, that is this, and that becomes 22, the sum of these two. Similarly, this is the sum of these two, and this is the sum of these two. So if we need to get sum of indices from like 1 to 5, what we do is we go down our segment tree, find the lowest element that corresponds to the range, like this. Then this also corresponds entirely to a range, 1 2 3. Then in this set, this node corresponds to a range. So we can divide any range in at most log n nodes, so we can do range sum queries in order log n time. So what's the benefit of such a data structure? Mm, 1 second. Hello, a body will Okay, we'll continue. So, what is the use of such a segment, such a data structure? Like, basically, personally, the best use I find is to first I need to define some words. Where is this audio coming from? So, um, this is a CP term, not related to general. A standard problem is something that is well known and doesn't require much thinking. So, like, if someone gives us a problem and we have seen it before, so we call it a standard problem that we can solve without much thinking. And there's some problems called cancer problems, adjective. So, like, these are the problems that do not require much thinking and they have a very long implementation. So, this segment tree helps us a lot of times to make those cancerous problems have shorter implementations, like diff to like in diff to C and D. So yeah, that's the main motivation to study segment tree and D for me. Other than that, there are some advanced version of segment tree like lazy segment trees and persistent segment trees. They help a little bit more in advanced problems. And to generalize the segment tree, we can basically do any we can basically make a segment tree on any operation that is associative. Like we can do range sum queries, range XOR queries, range max min, range GCD, LCM, considering it doesn't overflow, LCM doesn't overflow, and range multiply. This is what the basic implementation of a segment tree looks like. I have defined it in a struct form. So first I create a vector to store all our values, call it sum. I find the first uh, I find the first power of 2 which is greater than our input size, input array size. Then this is the build function. This is pretty basic. I mean, I expect viewers to know about this. If you don't know, there's a website. You can study the basics of the segment tree from here. I'll put this link in the description. And now I'll continue with the more advanced concepts. So, like, now we have a lazy segment tree. In a lazy segment tree, what we can do is we can do range updates instead of point updates. So, like, if we want to add a fixed number in a specific range, like continuous range, like here we are adding from range A to B. So like what we do is we put we store, instead of one number, we store two numbers at each node. One denotes the sum value and the other denotes the lazy value. Lazy value means like we have to propagate this value to the subtree nodes. I mean, this lazy value means that we have not updated our subtree nodes if it is non-zero. If it is zero, that means we have, if we had a previous update, then we would have already propagated into the subtree nodes. So like, uh, consider a range query in which we have to update, in which we have to range some elements from A to B by 2. So what we do is go left. This entire range in, does not lie completely inside A to B. So we go further down, further down, further down. We add 2 here. We go right, further down. Update the lazy value of this because we do not need to go further down as this node is entirely covered in the given range. Again, this node is also entirely covered in the given range, so we just update its lazy value to 2 and its original value to 20, and we go here and update its lazy value to 2 and original value to from 6 to 8. So um, now I'll show some problem on a lazy segment tree. So first I'll explain the problem. We are given n pairwise distinct points and line x plus y equal to h such that all the points lie strictly below this line, like less than to that, all the points that have x plus y less than equal to k minus 1. So we are given n such points and we have two kinds of operations. Either we can draw a triangle, any triangle that touches the given line, and let its length be L, L and root 2L. So what we can do is remove all the points in this range. Our task is to remove all the given points in the input. First method is this. We can draw a triangle, remove all the points in this range. The cost of this operation is this length times a given input A. And second operation is we can just use any random point of our choice and erase that point. So I'll give you 2-3 minutes to think. What we have to do is to minimize the cost. The second operation costs us CI points, and the first operation costs us L times A. So I'll continue now. There are mainly two observations in this problem. First is that let's see that let's assume that this is the line. Then if we make a triangle like this of length L1 and we make another triangle like this of length L2, then if they intersect, it is not optimal to erase points like this. We could just make a triangle like this with length less than equal to L1 plus L2 and remove all the points in this entire range with cost less than equal to A times L1 plus L2. But this would result in a cost of A times L1 and this would result in a cost of A times L2. So it would be better to just erase a length of their intersection and we cover more points with a less cost. So it is never optimal to choose to choose two intersecting triangles. So what we will always do is choose some non-intersecting triangles to erase the points, and all other points that are not lying in our triangles we would have to erase them using the second type of query. So let this be our coordinate axis. So what would be the brute force method here? We could just pick some points, pick some dp, let's assume dpi to be the dpi to be the like we have covered all the points with x coordinate greater than equal to I, and the minimum cost to the minimum cost required to cover min cost required to erase all this we are. So if we assume this to be the DPI, then how would we update our DP state for DPJ? What it could be is we try to make triangle for every possible x coordinate greater than I, and we would have to erase all the points which are lying below this triangle, since they would not have been covered by any triangle after that. So it's like, let these be y points. So we would apply c times y, ci times y for these points. Summation ci y. The cost of removal of these points will be summation of ci y. So dpj, the transition states for our dp would be like dpj equal to minimum k greater than I dpi plus summation CIYI such that x coordinate of yi is greater than k. Let this be some other variable CLYL such that YLX is greater than k. So obviously this seems to be an n squared EP. There can be n such points and there are n transitions. So at least it is order n square time. So how could we think of improving it? One method is that, like, let's say we have found dp I till now. When we move from I to I minus 1, what we would need to do is, like, let's say there are points at y coordinate of y1, y2, y3. So consider how um, consider the triangles that could be made from all the further x coordinates that we could ever reach. For dp, if we minimize the dp for that, let's call it d, let's call it k. If we choose to minimize dpk using this I, then we would need to add, if y1 is less than this corresponding y coordinate for I, then we would need to add this c1 y1, the corresponding cost for removing this point, into dpi. So all the y points that lie below this line, they must be added into dpi for considering it to for considering it for this minimization. So one thing we can do is, like, iterate over all the y or iterate over all the points that lie with x coordinate equal to y minus 1, I minus 1, and let's say that we are at y equal to something, why not? So we find this coordinate. We find the corresponding x such that the triangle for all, let this be x star. We find this x star such that the triangles made by all the dp states could not have an endpoint above this less than this x star. That means all the dp states such that the triangle made by them could not have the left endpoint less than x star. So that would be all the dp system m greater than x star. So that if we had a point at y equal to y naught, we would need to add this the corresponding cost, let that be c dash. We would need to add c dash into all the dp elements that lie in this range. So what can we see here? This looks like range sum queries. So we need to add this cost into this range of dpa. We need to add this cost into this range of dp array. So when we are at this point, we take its cost c dash, range sum it into this dp array. Then this dp array will be updated for the minimization. So when we are at y1, we add the cost into this range. We add its cost into range that store this dp. When we are at y2, then add this range. And y3, then add y3 has the y3 is there at the bottom. So like it would always be covered. And also like when we have to make a triangle from here to there, once the x coordinate decreases by 1, the triangle size also increases by 1. So we will need to add a to all the dpi's. So the transition state is like for all the points, add the for all the points yi's, find the intersection, add their cost into this dp range. One second. I'll just do my code now. The idea I've already said. Here is the segment lazy segmentary implementation. This is the part for merging. I need to take a screenshot. This is the basic segmentary implementation. Notice how I have made specific functions for merge and propagate. This what this merge function does is once we have evaluated the values children of the children nodes, it finds the value for the parent node. Here we are doing minimum operations, so we are taking the min of the values of the children nodes, and the lazy tag is set to 0, meaning we do not have to process any queries further, process any updates further. And here the is the propagate function. What this propagate function does is it this is the lazy tag of our current x coordinate of our x node. So what it does is it increases the value of each children by the lazy tag because we were doing range sum queries. So here it increases the tag by plus equal to. If they were range set queries, we would not have this plus. And we also update the lazy tag of the children because they could also further update their children values. And we reset our lazy tag of current node to 0. So this is one easy way to implement a lazy segmentary is to make these merge and propagate functions, then implement the further functions. So like once we are doing range update, always propagate the node first before going into the subtree, and for merging them we can just call one single function and merge them. And while querying something, we also propagate before going into the subtree. So here I just taken the input and initialize the lazy segmentary. The x coordinates are in the range k plus 1, initialized by 0 because minimum initial answer should be 0 when we have not when we have not deleted any points. So inputting the pairs, uh, iterating from the rightmost x coordinate to left. This is the iterating over points part. We update give the required range that I mentioned. This is the vertical line. We have we are at this coordinate. Let these be the points with x coordinate as the same. Then we find the intersection with this line. So like when we make a triangle from any coordinate to here, let's say from any coordinate to a farther coordinate, this point will always be covered for all these range. This point will always be covered for all these coordinates. Similarly, this point will always be covered for all these triangles, because once we try to make the triangle from here to here, this point will be inside it. And again, if we try to make a triangle from a further point, this point will again be inside it. But if we try to make a triangle from here to a x coordinate before this point, then this point would not be included, and we would need to delete it using the cost of this point, that was CA. So we need to update we need to add CI to all these coordinates. Similarly, if this is CJ, then we add CJ to these coordinates. So by iterating over points, this is the cost of it. This is the all the segments after current coordinate. This is the intersection point. So I increased the dp value in this range by c. Then we are just taking the minimum. And we are setting the ith coordinate dpi with this minimum. This curve variable is basically if we do not make any triangle. Curve is always updated by this. So curve is the minimum dp value till now. Curve 2 is if we delete all the points manually without making any triangle. Curve 2 is increased always by c. Then we minimize the dp value by this curve 2 if we do not make a single any triangle. So we update the dpi, and here we add the a value to all the dp arrays, because any further triangle from them would have a length greater than 1 from now on. So minimize the answer. In the end, we just output the answer. So this was like one simple implementation of lazy segmentary, and as we can see, the problem is 2300 rated. So the segmentary problems are usually inflated in rating. So if you know the data structure, you can easily solve higher rated problems. That is one thing about these standard problems. Many authors tend to put a lot of standard problems thinking they are good, but those who have seen it, they just copy paste and submit instantly, get free rating. And those who have not seen it, they just lose a lot of rating. So, there is one more type of lazy segmentary I should discuss. In that, in this we were just showing range sum and finding the minimum in a range, there's a special kind of segmentary in which we can do range sum, and within a range we can ask for the minimum element and the frequency of it. So like, let's say that this is our array. In this range, the if we input this range, it will give us 0 as the minimum value and frequency of it as 1. If we input this range, it will give us the minimum as 1 and the frequency of it as 2 because it occurs twice. This is 3. So, to prove that it is possible, we can see that it is an associative operation, because like if we have two different values, the min value and the frequency value of this, and the min value and the frequency value of this, we can find the corresponding min comma frequency for their combination array. Like if we join these two ends, we can find the corresponding minimum and frequency for this whole array. The minimum will be the minimum of those, and the frequency will be the corresponding frequency of the minimum. If like this is less than this, then this frequency will go here. If this is less than the other one, if this is less than the other one, then this frequency will go here. If both are equal, then we would just add the frequency and set it over here. Like, this is one common variant of lazy segment tree which many people don't know about. Let me find its implementation. So in this version of segment tree, in each node we store three different values instead of two. First is the minimum, second is the frequency, and the third is the lazy tag. The merging is like I told, if they are same then we add the frequency. If one is less then we um, take its corresponding frequency and value, otherwise the other one's value. And the propagate is also similar here. Yeah, so This was the main part of the implementation. Not there are not many other changes. So what is the use of this segment tree? Let's say we have an array. Um, there have been some problems like in last years, last year's Asia West, where there was an array. We had to decrease. Uh, we could find some subarrays which were bad, and we had to find those indices such that they are good. So like we were given some subarrays. The union of them will be bad. We have to find those indices which are good. Like if we iterate from right end to left end, let's say we are at current index, then we unlock some subarrays which are bad. So we have to take union of them, and one second I'll find the exact problem. So a subarray is considered good if each element in it appears a power of 2 times. So let's say this is our array. We can start iterating from the right end. If we are at this index, then we will consider the power of one array. This the range where this element occurs only one time, that will be this. Then we consider the range where it occurs two times. So like what we can do is we can find all the bad subarrays corresponding to this element. We can increase one in that subarray and then count the all the indices that are equal to 0, because 0 will be the minimum. If a subarray is bad, we would have added 1 into that subarray. So initially all elements were 0, so minimum will obviously be 0 since there are only addition operations. So what we can do is add 1 into all the bad subarrays, then find the minimum using this segment tree and the frequency of it. So we get the corresponding right ends for the current left end that are good. Like if we are here, if we are here, this the range till which it occurs one time is good. Then let's say it occurs second time here. This is the second occurrence of it. Then let's say this is the third occurrence of it, and this is the fourth occurrence of it. And this range will be good corresponding to this number. This range will be good corresponding to this number. This range will be bad. Let's make this 2 1. So what we will need to do is add 1 to this range, because this range is bad corresponding to this number. There will obviously be order log n ranges, because frequency of any element is limited by n. So we will need to do order of log n updates. When we encounter this number again, we would need to revert this changes and make the changes again for this. Like this is good. This is the first range that is bad, and this will be the second range that is bad. So the, at each step we will need to do order of log n operations of incrementing one into a bad range and finding all the indices for which the value is 0. And that will mean that that right end corresponds to a good array, corresponds to a good subarray, and we get all the right ends which are valid with our current left end. So this was also a standard implementation problem, cancerous implementation problem. Next, there is also another kind of lazy segmentary in which, let's say we have an array, we have to find the summation of x raised to power I. X raised to power, let's use another variable, summation of ai raised to power k. If this is the array A, we have to find summation of ai raised to power k over an interval L to R. And obviously this includes updates. We could add ai, we could add 1 to ai, like we could set ai to ai plus 1, or in general we could set ai to ai plus u. And since it is a lazy segmentary, we can do like for all I belonging to L comma R, do ai to ai plus u, and we have to, and once we are given a L dash comma R dash query, we have to output the summation of ai raised to power k in the given range, L dash to R dash. So this is the generalization of the range sum segmentary. This one thing we need to have is that the k should be small enough, like k less than equal to 10 or something. So the idea behind solving this is that summation of once we add, let's say we have currently summation of ai raised to power 3 in the subarray. We have summation of ai raised to power 2 for the subarray, and we have summation of ai raised to power 1 for the subarray, and we have to add u in some range. So what we would do is, let's say this is our segmentary. Then for the corresponding range, we will update its nodes. Let's say that this is the range. Then we would update this node and this node. let's say we have these all these values for all these nodes. So if we have to update this node, then what would we do? Like, observe one thing: summation of ai plus u का whole cube is equal to summation of ai cube plus 3 times summation of ai square times u plus 3 times summation of ai times u square plus u cube. This is the result of the binomial property. You can try to expand it and add all the terms individually. So if we have all these stored, you also need summation of a raised to 0 called. So if we have these four values, we can update summation of ai whole raised to 3 using these previous values of these. So this can be generalized for any power using binomial theorem. So if we have ai is for I, so if we have all these summation values, we can update summation of, we can find the new summation of ai raised to j using all these values. Let's call the new summation equal to x raised to j. Let's call this small x j, small x j minus 1, where this is x0. Then if this is the new value that we have to found, updated value after adding u into the whole range. Let's call it xj. Then this value will be equal to jc naught xj plus jc1 xj minus 1 plus jc2 xj minus 2 plus jcj x naught. So using these values we can find the updated, oh sorry, not this, multiplied by u multiplied by u square multiplied by u raised to j. So this is the general method of finding the updated value of summation of a raised to j. We can do one by one for each power and update all these values one by one using the previous values. So the summation of an update will be order of k square. This was the k, the limit on the power. So an update will be of order of k square login instead of the usual order of login time. Yeah, so this was another kind of segment tree in which we need to range some power of the array indices. There aren't many specific ad hoc type problems for this. Usually when this segment tree comes, they directly ask you to compute this summation. So this results in the most standard problems I've ever seen. Next, we will do persistent segment trees. I'll do some problems now in the end. So, like a persistent segment tree is a normal segment tree, but in that, what we can do is once we update the value, once we update any value, we can still access the history of the segment tree. Like once we have made a change in a value, it doesn't matter like that we have changed. If we want to access the older segment tree, we can do that also. So the downside of this is that the memory increases. In general segment tree, in normal segment tree, the memory is order of n. In this segment tree, the memory is order of n plus q log n, where q is the number of updates. So since we have order of q log n memory, this can reach quite high amounts. Like q can, if q is of order 1e6, log n would be of order 20, let's say. Storing 1e7 numbers requires quite a lot of memory. So one needs to be aware of the memory limits of the problem for using this segment tree. Also, the constant factor is also very high. Like we need to store 3 to 4 numbers, so we would require 3 7 integers almost. So now I'll tell the basic idea behind a persistent segment tree. So let's say that we update this node. So once we would need to update the top node for it, and this node for it, and this node for it. So what we do is, instead of changing these nodes, we create new nodes. Like this node is created, its left node is the new other created node, its right node is the second new created node. So and we can do is, for its right node, instead of for its right children, instead of creating another node, we can reference it to the older segment tree. Like this is our new head for the second step. Left subtree will need to be updated, so we create a new node for it. Right subtree can be remained as the same. We do not need to change it, so we can reference the right subtree to this subtree. So since each update requires only order login updates, we need to create only order login new nodes. So In each node, we store the node storing the left subtree and the node storing the right subtree. In the third step, if we update these three nodes, then notice that since this is the third step, these updates are performed after step 2. So the left subtree for this would be the left subtree of this node. So the left subtree is pointed to this node, as we can see here. The right subtree is pointed to this new created node, and the left subtree of that is pointed to this old node, because the right subtree of this was this node and the left subtree of this is this node. So yeah, that's the basic idea behind a persistent segment tree. That do not make all the new do not make the entire segment tree itself. We can just make order of log n nodes again and keep the previous nodes as the unused subtrees that do not need to be updated. So this idea can be generalized to many other data structures also, like a persistent trie. I've heard some people make persistent DSU, but not like persistent least chaudhary, and there are many persistent data structures. The same idea can be generalized to many places. So what is the benefit of it? One benefit is that we can add an extra constraint to the problem from this. Since we have all the previous history, if we have a problem in which we have two constraints, we can solve one constraint using the history of our segment tree and another using the segment tree's properties. So, like, if we need one example is like if we need to find the number of elements in some range L comma R that are less than equal to y. Y is some given input number. So we have three inputs L, R, and Y. We have to find the number of elements in L comma R that have value less than equal to Y. What we can do is initialize a frequency table to 0. Once we iterate over the array, like let's say this is the array 1, 2, 3, 4, 1, 2. Then what we do is we go to this node, update this value, ask the segment tree to update this value to 1, update this value, increase this value by 1, the frequency of 1. Then when we increase the left index by another amount, then we check the AI, that is 2. We increase the frequency of second position. Then when we are here, we increase the frequency of third position. When we reach here, we increase the frequency of fourth position. Then when we are here, we increase the frequency of first position again. So now this becomes 2. When we are here, again this changes to 2. So let's say we are given this L comma R that are less than equal to M. What we can observe is that we need to find this query can be reduced to another type of query. Number of elements in 1 comma R less than equal to Y minus number of elements in 1 comma L minus 1 less than equal to Y. So what we can do is take the rth version of segment tree, find the range sum in the range 1 comma y, and access the L minus 1th version of segment tree and count the number of elements in the range 1 comma y. Let this value be x, let this value be a, let this value be b. Then we will output the answer by a minus b. So another version of this segment, another use of this segment tree could be find the number of occurrences, find the number of occurrences of some number r. So this is basically the another version of the previous query. Like we could find the range, we could find the number of elements in the range L comma that are less than equal to x, and then again we can query number of elements in the range L comma that are less than equal to x minus 1, and just subtract both to get this answer. These are two useful applications of persistent segment tree. Now I'll show the basic implementation of a persistent segment tree. So we have a node. The left variable shows the left index, the index of the left node. The R variable stores the index of the right subtree, and the value stores whatever value we need to process for our segment tree. This could be the range sum, range minimum, range max, BCD, LCM, whatever. And like I have initialized a big array of size 2 is around 2a6 to store all the nodes of our persistent segment tree that can be made in the further process. This cur variable shows like how many nodes we have created yet. So we have a build function to initialize our segment tree. Makes a left subtree, makes a right subtree, and then initialize the left subtree and right subtree iteratively. This is the add function. If the this persistent segment tree is to add a number in at a specific position and find the range sum. So like it is point, it is point set range add. So like we are setting some value at a specific index, and we can query range sum in some range L comma R, find summation of AI. So here you can see I add only one new node for the left subtree, reference the old one for the right subtree. In the other condition I add for the right subtree node and reference the one for the left subtree. And the get function is the same as the older one, as for a normal simple segment tree. Right, so now I can talk about some techniques of segmentaries. There is one common technique in a segmentary. Let's say we have an array, we have an input array, we have to find some specific value. What we can do is we do not initialize the array itself. We can iterate over the elements in some specific order and update them accordingly. Like we could iterate over the sorted version of the array and update the segmentary the, while iterating. Do not initialize at the beginning. Update it while iterating. So what this results in, we can reduce an extra constraint using the iteration property. Let me find a problem for it. So we have an input. Uh, we have an input permutation. We have to find this value. Our di array denotes the minimum value of mod of pi minus pj plus mod of I minus j for all j is not equal to I. So we have to find this value for all I. So the method for this is like if we had initialized the whole p array in a segment tree, then that would be of no use to us. What we do is iterate in the ascending order. Like once if we iterate in ascending order, consider this di value for some pi less than pj. This will be pj minus pi plus mod of I minus j. So like we can initialize a segment tree, initialize all values to positive infinity. We iterate in the sorted order. What we do is like once we are at pi, only those values should have been updated for which pj is less than pi, for which let's say we are at pj, then only those values would have been updated for which pi is less than pj. So the value we know directly, the d for it would be pj minus pi plus mod of I minus j. If the index is less than current index, then what we would have done is we would have updated this pi with pi um, negative pi plus negative pi minus j, because if I less than j and pi less than pj, you consider these two cases. So we would update it with negative pi minus I and find the minimum value in this range, and then add pj plus j to it, and we would get the required value, pj minus pi plus j minus I. Similarly, we iterate for I greater than j and pi less than pj, and similarly for I less than j and pi greater than pj, and I less than j and I greater than j and pi less than pj. So we divide this into four subproblems, iterate in the increasing order or decreasing order depending if pi less than pj or pi greater than pj. For these we would need to iterate in ascending order, and then we for this for first case we update all the elements by negative pi minus I, and for the second we update by negative pi plus I. For this we update by pi minus I. For this we update by pi plus I. So by dividing this problem into four subproblems and iterating in a specific order and updating the values in a specific order, we can use a simple segment tree to solve this problem. Another technique is walking on segment tree. Like in general, what we do in a binary search is we have, we have some property over a range, some monotonous property, and we have to find some prefix of the array. Uh, like we have some prefix of the array satisfying some property, and every element after it does not satisfy that property. So for bin searching, we like find the first element in the range that does not satisfy the property. So for a segment tree, what we could usually do is query individually for each 0 to mid range. That would take order of log n time. So general binary search on a segment tree using normal queries would take order log square time, because log n of the binary search and log n of each query of the segment tree. So how we could improve that is we could start from the root node of the segment tree, checking the value of its left subtree is equivalent to checking the value of the range 0 comma mid when L equal to 0 and R equal to n, and if this satisfies we could move to the right subtree. If we are finding the first element which does not satisfy the property, if this range satisfies the property, we could go to the right subtree. Notice that this checking that this range satisfies the property takes order 1 time instead of order log n time. So if this satisfies the property, we go to the right subtree. Then the binary search range reduces to L equal to mid plus 1 comma n, R equal to n. If this would not have satisfied the property, we could go to the left subtree and our range would have reduced to L 0 comma mid. So again we check for the left subtree. If that does not satisfy, then we again go to the left subtree. Otherwise we go to the right subtree. So this is a faster version of doing binary search on a segment tree. Instead of querying individually for each step, for each iteration of binary search, directly start from the root node of the segment tree and walk on the segment tree. We are basically like walking from here to here to here. So this is called a walk on a segment tree. So the benefit of this is it reduces the binary searching time from order log square n to order log n. So now there come problems which combine these all these techniques. Like there's this problem. This problem uses a persistent segment tree and this binary searching by walking on the segment tree. So what this asks us is it gives us some ranges, and we have to find the smallest number in this range in the input array that occurs an odd number of times. So this was a diff 2f. They are the ones that usually have standard problems. So like the method is to first we make an observation that if an element occurs an odd number of times, then let's say there is an element that occurs in the range 1 comma L odd number of times, then the XOR value of it will be will be not equal to 0. The XOR value of this entire segment. So like you can generalize if an element occurs an even number of times in the range L comma R, then the XOR value of the range L comma R, like if every element in the range occurs an even number of times, then the XOR value of this range will be equal to 0. If any element occurs an odd number of times, then the XOR value of this range will be non-zero. So what we can do is initialize the prefix XOR array. Let me paste the solution so I can explain it simultaneously. So first we sort this array in ascending order. So like let's say that this is the ascending order array for a prefix L, and this is the ascending order array of prefix R. But we store at each index is how many times the element has occurred. Like let's say if an element has occurred two times, the smallest element has occurred two times from 1 to L, and from 1 to R it has occurred three times here. So basically over all these arrays we have to find the smallest element such that let's take it L minus 1 if the query is L comma R. So we have to find the smallest element for which R, the frequency of it in prefix 1 comma R minus the frequency of it in the prefix 1 comma L minus 1 is odd. Then only it will occur odd number of times in the range L comma R. So since we only care about the parity, we can replace it with XOR. Like if it had occurs two times, we could replace it with 0. So in this, the smallest element occurs one number of time in 1 comma and 0 number of time in 1 comma L minus 1. So the smallest element of array will be the answer if this was the frequency table. Frequency is all table. So like this, finding first element which is not the same, which is different in the two segment trees, is like binary searching on the segment tree. We start from the top node and find the first element non which is not equal in the segment tree. So like what we can do for checking if there is exists a different element in this entire subtree, in these two subtrees, like take the XOR of all these ranges. Like let's say this range inverts to this inverts to this range. What we can do is take the XOR of all these numbers. If that XOR is different from this to, if this is different from this, if the XOR value for this range is different from that of this range, then we know for sure that this subtree contains at least one different element from this subtree. But if but XOR can also be XOR can also be same even if the elements were different. For that we use a probabilistic approach. I will tell that later. So first approach was that if the subtree XOR is different from the subtree XOR of this, then we know for sure that this subtree contains a different number than this subtree. So we can choose to go into this subtree, otherwise we go into the right subtree. So to avoid false negatives, what we can do is replace each number with a random number in the range random number in the range 1 comma long max around 918. So for that, if the XOR of A1 AI XOR, so the probability that A1 XOR A2 is equal to some A1 XOR A3 XOR A4, basically XOR of some different elements is equal to XOR of some different elements, will become quite small. So I'm replacing these elements, like if the smallest element was mapped to 99813 instead of 1 here, we will store this value here, and if this was also 1, we would also have stored this value over here. So while range XORing, we XOR this value, and while updating the frequency, we also XOR this to this. Like if we were adding 1 in our frequency table, then instead of adding the index by 1, what we would do is we XOR the index by this value. So like for checking if a subtree is different, for checking if two subtrees are different, we can just compare their range XOR values and conclude that if they are same, they are equal subtrees. If they are different, then they are different, with a very low chance of failure. The probability can be calculated in a way like around 10 possibilities there are for collisions. So probability will be around 1e minus 9 for a false negative. 1 in n is a quite a small probability. So yes, the final approach is make frequency tables for prefixes, but instead of frequency we store the XOR values and range XOR, and checking for finding the first value that is different in the frequency tables, we binary search on the segment trees. We binary search on the segment trees for the range 1 comma L minus 1 and 1 comma R, and find the first index that is different in both. If no such index exists, then all element occur even times. Otherwise, the index, the element corresponding to that index occurs an odd number of times. So this is the implementation. First I make random hash, then here I initialize the persistent segment tree. Here I update the frequency tables by hash of that index, add the position of that index. The J stores the position of that element in sorted array, and while the input is given, so I find the first position which is different in both segment trees, so that element occurs an odd number of times, and output its value. So as you can see, This problem was mainly template related problem. The main implementation is like of only 25 lines at most. So this is an average standard problem. One thing I would like to stress on is that notice that how I've made a vector of nodes instead of some people use pointers instead of integers. Like instead of intel they store node char l and node char r. These are pointers to left subtree and right subtree. The benefit of using integer values is that first integer are 32 bits. If you are on a if you are on a 64-bit system, these pointers will be of 64-bit, and already persistent segment trees use quite enough memory. This would directly increase the memory consumption by twice. And also, there is a reason of compiler optimization. All these nodes are all these nodes will be located in a continuous range. But if we use these pointers to store the left subtree and right subtree, then when we update and make new nodes, they will be scattered randomly in our memory. So accessing them can take a quite a lot of time instead of just accessing elements in a continuous vector. So like, there were two benefits. One was memory and one was continuous allocation. Notice how there are three variables instead of just one. So it takes 76 times three integers. So that requires quite a lot of memory. I think my solution took, yeah, 95 MB memory. So you need to be uh, quite careful about the memory limit of the problem. Like recently in a div2 there was a problem which was very simply solvable using a persistent segment tree, but the memory limit they kept was 256 MB and n was 1e6 in it. So if you use a persistent segment tree, that would result in over around 87 integers. So that would easily result in MLE in 256 MB. So yeah, that was a bamboozle by div2 authors. Very rare. Some people did manage to pass persistent segment in that though using shorts and whatnot. I mean, some people are like that. They spend their lives optimizing the codes to the slightest of the memory limits and time limits. Like their codes would run in 255.5 MB. And then there was this problem which utilized the property of lazy segmentary and bit sets. So the two most cancerous topics that are used frequently in recent times. So I won't be explaining much. No, I'll just tell what I did. We had a what we can do is make a bit set of bit set storing values, and the use of bit set was taking intersection and union of sets and counting the number of elements in a set. So intersection can be taken using and equal to operator in a bit set, and union can be taken using an or equal to operator in a bit set. So that's how you merge. For merging also you can take we needed intersection for merging, so I took the and operator on a bit set. All these are all these are storing bit sets. So yeah, so this is how we can do set union and set intersection queries on a lazy segment tree using bit sets. Time complexity would be order of n log n times size of bit set divided by 64 or 32, depends on the specification of the system and whatever optimizations you make. And then there's this problem. This was lazy segment tree range sum combined with binary searching using walking on segment tree. So, but in this problem, it was possible in n log square n time also because memory, because time limit was very reasonable. A similar problem occurred later with the name M3. I think it was named M3. Yeah, this problem. It is the exact same problem. It uses the idea of range sum and walking on the segment tree, and just just using that you get a problem with the rating of 2800. Like, why are they putting such trivial problems? And also, obviously, the implementation is very tough. Like today, I tried to implement it, but I failed. Even I failed. You can see how cancerous the implementation is. Just for this, people are getting LGM performance. So yeah, that's it from my side. So a short recap I'll give the techniques that I mentioned in the video. Lazy segment tree. One was finding summation of x raised to power I, summation of ai raised to power k in the range with k less than equal to 10, with updates of the of like of the form for all l comma r, set ai to, and queries of the form. So we are range summing of, we have to find range sum of ai raised to power k. So this was one technique. This was one type of lazy segmentary. Another type of lazy segmentary was finding the minimum element in range and its frequency. So these were the two types of lazy segmentary I covered. Two layer types of. And then I covered persistent segmentary. Their uses. And then I covered some techniques. Updating a segment tree in a fixed order to reduce some constraint. Second technique was binary search by walking on subtree. Then I should set union range set union and intersection updates using bit sets. So yeah, that was the overview. I will put some references in the description if you want. So if you have any questions, you can comment in the chat box. So there was a question that there would be at most two elements which would be immediately updated. Yeah, that is true. Like in the array, we can update at most two elements directly. Rest all the updates will be in the nodes in the subtree that cover the entire subtree. Like they would not be part of the array, but some nodes which would be covering some ranges. The camp is available for some selected values. Yeah, some problems are solvable without lazy. We can always do some mathematical manipulation and turn lazy into normal segment tree also. But that just results in useless, more implementation. So I prefer to use lazy segment tree over doing some mathematical manipulation and using normal segment tree. Like in the last contest, it's good for this jump. So basically, in the last contest, I had used Secretary for C and D just to skip implementation, skip useless implementation. So that is one big use of segmentary. So yeah, I'll end the stream now.